Good morning.
Hello.
Hello, Eleanor.
Hello, Nicholas.
Just confirmation from James that the visual and audio are both working fine, and the recording has also begun as well. So good luck, guys.
Thank you, James. Nicholas.
Yes.
I don't know if James started this yet. Okay, we'll start. Good afternoon. My name is Eleanor Mackay from SJP Business Media and Electronics World. As a company, E2V partners with its customers to improve, save and protect people's lives. Its innovations lead developments in communications, aerospace, discovery, healthcare and the environment. In this webinar, in association with Electronics World, Nicolas Chantier of E2V will discuss introducing software-defined microwave systems and pushing the boundaries of RF to digital frequencies. Should there be any questions, Mark Stackler, Application Engineer at E2V, will assist Nicholas answering all questions at the end of the presentation. Over to you, Nicholas.
Hello, thank you, Eleanor. Welcome everyone on this webinar. We'll be starting. I hope everybody can see my slides. I'll move on to the agenda slide. So on the agenda, I'll be covering 7 topics, so actually 6 topics. Simplification of the RF signal chain, multi-nitride D2A converters. We will look at then point number 3, multi-nitride D2A converters and their bandwidth limitation. That's an important thing to understand when we design software-defined microwave systems. We look at pre-distortion to seek for flat frequency response. We look at DAC output power versus nitride zones and different operating modes. And we look more closely at the case of one particular DAC, a recent release from E2V, EV12DS400, and its measured performance. And we'll probably look at some application example as well. And we'll be open for questions. If you have any question post-webinar, we remind you the email address of our application engineer, Mark, who's here, and also Roman Stackler, Roman Pilar on the team, who will take any technical questions after the webinar. I have moved to slide number 3. So I'm moving my control over here. So on this slide, we make a comparison between traditional system at the top of the chart and what is enabled in terms of software-defined microwave system with latest generation D2A converters. So with the emergence of ultra-wideband DACs that are capable of operating at microwave frequency, that enables the simplification of RF hardware, obviously. A lot of what previously was required to be built in as complex RF hardware can now be done in the software domain. So we see at the top we had many channelization to achieve wide bandwidth. We had to separate that in many channels, made large real estate requirements and lots of channels that can now be done with one ultra-wideband device as shown in the at the bottom of the chart. And also a lot of the frequency conversion, mixers, and a good number of the RF circuitry, good parts of it, can be done in the software domain in the DSP unit at the bottom of the chart. So that simplifies significantly the RF signal chain, as you can see on the diagram at the bottom of the chart. Okay. Moving to slide 4. There, it's a reminder of fundamental things that we need to understand when we use digital to analog converters. At the top of the chart, figure A represents a typical sine wave, obviously, with the vertical green lines will be sampling points. Figure B is a digitized representation of it in time domain, and which obviously with high resolution DACs has finer steps which can be so fine that we actually don't see them on a screen representation. But here, for illustration purposes, they are exaggerated so that we can really see the digitization and the quantization steps. At the bottom of the chart, figure C is a frequency representation of a sine wave, as well as the output power versus output frequency, when we use a perfect DAC, and that's after digital to analog conversion. What is important to look at, I suggest you pay attention to the various night width zone, NZ1, NZ2, NZ3, NZ4, NZ5 that are represented at the bottom there. Looks slightly above them, you'll see the half frequency, sampling frequency line that is shown for the limit of first night width zone. So if we look at night width zone 1, we see a big solid line through the beginning of the night width zone, which is a sine wave. When we look at the second night width zone 2, we see an image of that as images which are shown there. It's important to understand that on even night width zones like NZ2, NZ4, the spectral representation is flipped. So what was a low frequency night width zone 1 is towards the high end of the night width zone in night width zone 2, and vice versa. It's like a mirror effect. That's what we call the images. It's important to keep this mirror effect in mind, because when you define the content of your which signals you put inside the night width zone, it's important to understand that there is this mirroring effect if you choose to work in night width zone 2 or night width zone 3. Okay. Moving to slide 5. I think I need some time to update everybody's screen. That's probably done now. Slide 5, we're showing on figure D, we introduce the idea that DACs are not perfect. Their output stage behaves like a low-pass filter. We see the case of DAC1, which I'm showing a very simplified representation of the output stage frequency response. It would cut off, it will be the first one to cut off that some frequency that needs to be defined. If we compare to the bottom chart, it's after in the second night width zone, it's cutting. DAC2, which could be a similar DAC, but would be in this example a DAC with a much higher output bandwidth. It would behave, its output stage will behave like a low pass filter, cutting off after in the fifth night width zone after 2 times sampling frequency, 2 times FF. It's important to keep in mind the fact that DACs have a cutoff frequency. Most of the DACs they are designed to cut off in the second night width zone, third night width zone. Sometimes it's not done on purpose, sometimes it's done due to the technology. But the latest DAC that we've developed at E2V are interesting in the sense that they have a very high output bandwidth in the range of 7 gigahertz. So that's a pretty high cutoff frequency. It's the example we show on DAC2 here. And what this means is that the output of a DAC, you have now multiple night width zones. Night width zone 1, 2, 3, and 4 are fully fitting inside the bandwidth. Night width zone 5 is where the output stage low pass behavior will start to cut off. Okay, that's something that's very important to understand. On the chart E at the bottom there, we also represent the output power versus output frequency, which is a phenomenon called sinc X or sinus X over X. It's classic with every DAC, but when we work often with DACs in first night width zone, because that's often the only night width zone that we can support, you don't really worry too much about the sin X phenomenon. It reduces the output power towards the end of a night vision number 1. But if you don't work in night vision 2, 3, 4, you don't really suffer much from that. Now, if you work in multiple night vision with that, you really have to understand this phenomenon of sinc X or sinus X over X, because it really affects in a significant manner the output power that you will have at the output of the DAC. So it's just reminding the basic thing. I'm moving now to slide number 6. Just waiting for you to have it on your screen as well. There we go. It's the simplified idea of pre-distortion. We can look at this in many ways. But before the DAC, on chart F in red, I'm showing the effect of the sin X over X phenomenon, which is a reduction of the output power towards the end of the first Nyquist. That's a natural behavior due to the sin X over X phenomenon in one output mode of the DAC. In chart G, in blue, we're showing the reverse effect of that. And this is something you can define in the software domain, in your FPGA or signal processing unit if you choose an ASIC instead of an FPGA. And what's interesting is when you multiply F times G, you have an H at the bottom there, which is a flat frequency response. So that's a technique that is used to compensate for the sinus X over X phenomenon of the output of a DAC. Obviously, when we choose to do this, there are trade-offs. Usually the available output power is reduced to some extent, but the big benefit is to provide flat frequency response, really. Now move on to slide number 7. I'm just giving some time for this slide to come to your screen. There we go. So there we show that that's as per the latest one from E2V, have 4 different output modes with different profiles of output power versus output frequency. They are shown here in the frequency domain. Obviously, they can also be represented in the time domain. And this is very useful to work across multiple Nyquist zones with DACs which have a high output power. That's why we pay attention to these modes when we design these products. So it's important to consider which mode is best depending on the Nyquist zone you choose to work on. That's really dependent on your system frequency plan. At the top of the chart, you see the NRZ, non-return to zero, and RTZ, the shape of these are purely dependent on the clock frequency. So it's directly related to the clock frequency, and these shapes can be calculated using formulas. So depending on which Nyquist zone you want to work, you can choose either one of these modes. At the bottom, you see the NRTZ, which is narrow return to zero mode, and to the right, the RF mode, so another mode. And there, what's important to understand is that the shape of these the frequency response is dependent on the clock frequency, but it is also dependent on the pulse reshaping parameters. So this is a new thing on the latest DAC from E2V that we have announced in December. It has pulse reshaping parameters that as a user you can change, and depending on the settings you apply, you will have a different position of the zero energy points. So if we look at NRTZ mode, or let's look at RF mode instead. So you can see the leftmost zero energy point is obtained with certain settings of the pulse reshaping width and pulse reshaping settings. When you change the pulse reshaping parameters, you can change the zero energy point to the left or to a different position. It's just an SPI setting on the DAC, and that's quite convenient to help you in the frequency planning. It works in a similar way in NRTZ and RF mode. It's just the overall formula is different. But these pictures are very important to understand if it's the first time you're working with multi-Nyquist on E2A converters. Move to slide 8. On slide 8, you will see a table that compares the different output modes. I'm waiting for this to come to your screen. There it goes, yes. So it gives you the ONZ, ONZ column, indicates the optimum nyquist zone for each output mode. So if you wish to work in the first nyquist zone, you see NRZ mode, NRZ mode is a good one. NRTZ can also be used. And it gives you a good combination of what are the optimal nyquist zones for each mode, the advantages of each of these four modes, and the trade-offs. What are the things you should pay attention to that need to be taken care of if you choose one mode or the other? And we also show to the left of the table the pulse reshaping features that are available depending on the modes. Okay. That's a simple summary table. Move on now to slide number 9. This slide simply describes the time domain representation of 2 of the 4 modes, as well as the frequency domain formula. So you've seen the shapes in the frequency domain. They are defined by the formula that you have on the left-hand side on the screen for each of these 2 modes. And we found the representation on the left is also interesting to show you the time domain behavior of each of these modes. On the next slide, slide 10, it's a similar representation for the other 2 modes. So there we are. NRTZ, now we'll return to 0 mode at the top and RF mode at the bottom. You see in time domain the pulses have a totally different shape, and the energy they provide in the RF domain is also very different. That's why also the formulas, the equations that we provide to calculate these output power versus output frequency are very, very different. And to help you make these calculations, we'll see on the next slide that we, excuse me, I'm just waiting for the next slide to come. We are providing simulation models. There it is, it's coming on your screen. Scilab models, some of you may know Scilab. It's an open source mathematical tool. Many are used to MATLAB. You could think of an open source comparable software to MATLAB. But this one is called Scilab, and we provide a macro that you can use in Scilab, which when you open it, it's screenshots number 2. It prompts you to fill in the various parameters, which mode of the DAC you want to use, the sampling frequency, output bandwidth, that's pre-filled in default with the 7 GHz of the E2V DAC, number of nyquist zones you want to plot, and the pulse reshaping parameters that are detailed in the datasheet. You can enter different values there and try and see what happens, and click on OK. And it will plot, as an example we show on slide on point number 3, it will plot in the frequency domain the output power versus output frequency that you obtain in different modes. And the example shows only one mode, but the macro will provide you plots for all of the 4 modes. And we think that's quite convenient for you to quickly have a look at the frequency response of the DAC in different frequency band situations, if you don't want to play with the equation manually yourself. Now we should be on slide number 12. Here on slide number 12, we show a simplified view of the fact that multiple nyquist zones are available at the output of these modern D2A converters. And that it's important to remember that this allows for removal of frequency up converters in L band, S band, and C band with current state-of-the-art D2A converters, 12-bit resolution. In this example there, because the latest DACs that we released at E2V have this low-pass filter cutoff frequency at 7 GHz, this 5th nyquist zone in this example here, when we got that 3 gigasample, the 5th nyquist zone is partially covered. So it's still available to be used, but you have to understand you have a reduced dynamic range fifth microzone. But for some systems, like synthetic aperture radar for 3D imagery from a satellite or from a UAV, it still is a sufficient amount of dynamic range, and it still can be a very good idea to design a system without frequency up converters and without mixers in frequencies up to 7, 7.5, or maybe up to 8 gigahertz as well. In slide 13 and 14, which are coming, just giving it a few seconds for everybody to see it. So here we show a theoretical example of frequency hopping encryption that is possible inside the microzone. I think it's important to talk about that, because these the state-of-the-art latest D2A converters at microwave frequency have amazing capability for frequency hopping. And keep in mind, this is a theoretical example. The real-life implementation obviously would have to account for bandwidth limitation and other constraints. But the theoretical example is still very interesting to understand. You can assume here a 20 gigabits per second data flow coming in at the top left corner into a unit inside your signal processing device, which will be a channelization. So you can channelize your big data flow into subflows, in this example from 1 to 200 data flows. That will then go into a switch matrix where you're going to switch data flow to channels, and the number of combinations being factorial 200. That's a very large number of possible combinations. And then that will go with feed modulation, channel modulations, which will then create 200 FDMA channels, which are represented at the output of the DAC at the bottom. So you see we have 200 little carriers, FDMA channels here. Each of them is one of the subflows. And if you wouldn't have this switch matrix there, flow number 1 could be channel number 1, flow number 2 will be channel number 2. But having this encryption switch matrix here, if you dynamically switch the assignment, like between the number of data flow and the channel number, doing this in your signal processing, you're actually doing dynamic frequency hopping in the frequency domain at the output of a DAC. And the number of frequency hopping combination is again in this example factor of 200. This is an amazing number. Think of the size of an microzone to give you an idea. When you clock at 3 giga sample, the microzone, which limits how many channels you can have in one spectrum, it would be 1.5 gigahertz. So between channel number 1 and channel number 200, you could have jumps which would reasonably be between in the range of 1.4 gigahertz. If you take a DAC like the latest ones clocked at 4.5 gigahertz, you could go work with the spectrums of a bit more than 2 gigahertz and do frequency hop of more than 2 gigahertz purely from software domain adjustments in your signal processing unit, and that's only within one microzone. It's very powerful. Now, put this into perspective with this following slide 14. I'm just giving it some time for you to see this. I think everybody should have it on the screen. You recognize at the bottom all the 200 channels that we have defined in the previous slide. You could choose in the RF domain now to route some channels to different bands. So in this, again, it's a theoretical example, but just to give you an idea of possibilities. In this example, we're routing the first channels to L band, some of the intermediate channels going to IF frequency, which is up converts to K band and X band. Some of us are routed to S band, some of us to C band. When you do this hardwired routing of channels in the RF domain, then every time you do change channel assignments in the switch matrix on the previous slide, you're doing crossband frequency hopping encryption across a very wide range of frequencies. And that's a purely software-defined frequency hopping system which is amazingly powerful, and which become powerful and possible now with the availability of microwave-capable digital to analog converters. I thought that's a very powerful example of what microwave-capable DACs enable. In some other applications, so that was with the idea of doing a data link and to secure it with frequency hopping encryption. In some other example, if you are doing, for example, for 3D imaging purposes, a synthetic aperture radar, all these channels at the bottom could be some signals that you turn on and off to increase or reduce your instantaneous bandwidth for imaging purposes. Now, it could also be software defined, and that could also be routed to different frequency bands to have a different radar information, because we know radar backscattering is different in L band and S band and C band. So that could make an interesting system, not only for data communication, but for other types of application that will be purely software defined and operating directly at microwave frequencies. Moving towards the end of the session, this is a summary of the latest DAC which has this capability coming to this. So EV12 DS400, we see that it has a 7 GHz output bandwidth, 4 operating mode as described before. A typical power consumption to expect from this DAC is 2.6 watts. It has 2 power supplies. On the output, this one has a parallel interface, a VDS interface with muxing ratio 1:4, 1:2. Following generations will have a serial input. The output in the analog domain, microwave domain, is 1 volt peak-peak differential, and all the settings are done through a 3-wire serial interface. For full documentation about this DAC and application notes and white paper, we've opened a product folder on e2v.com. That's the link that is shared at the bottom of the page, e2v.com/EV12DS400, and you'll be able to download all the documentation, including the Scilab simulation tool, the Scilab macro that we've shown before. In the following slide, I'll go briefly through some typical measurements. You'll be able to download this presentation and you'll be able to ask us questions about this. But this is an example of spurious-free dynamic range in the first NAC zone for this DAC. So we look first NAC zone in this case when we look at 4.5 GHz sample. It starts at 0 Hz and it stops at 2.25 GHz. And we have a carrier here at 2.2 GHz, and the highest spurs below are 63 dBc underneath, so it gives you a measure of the SFDR. On the next slide, 17, we see various measurements of these SFDR. I think I'm just waiting for everybody to have it on the screen. You'll see different SFDR values for different output frequencies, and that is in RF mode. It's important to understand different output mode of DACs will give you different response. So what you see on the screen is measured performance of spurious-free dynamic range when we use the RF mode at 4.5 dB sample. And for output frequencies which cover nearly the full output bandwidth of the DAC, starting at 0, 45 MHz, all the way to 6.7 GHz, we are very close to the cutoff frequency. Moving to slide number 18, some further SFDR measurements. In the second NAC zone. You can start to see it. So that starts at 2.25 GHz and stops at 4.5 GHz. And there the carrier is at 4.40, nearly 4.5 GHz. You would see the highest spurs with 61 dBc below the carrier. And that's been done in RF mode. If we choose another mode, we would see different performance. Slide number 19 is coming. That's IMD3 measurements in the first micro zone. So we have two carriers, one 2 gigahertz and one 10 megahertz higher, and the power is -8 dBFS. And we see image per 61 dBc, which can be lower than 61 dBc, which can be filtered if needed. It gives an idea of the performance ID of the IMD in the first micro zones. Slide 20, we are zooming into the two carriers and see what's happening closer to the carriers. That should be coming to your screen, yes, right now. So you see we have a 74 dBc standoff from the carrier to the closest spur when we are zooming into the carrier signals. On slide 21, some more IMD3, now with much higher output frequencies. So we're looking at from 4.5 gigahertz to 6, slightly above 6.7 gigahertz. We have one carrier at 6.5 gigahertz and one 10 megahertz above, and we see image spurs below 55 dBc, which can be filtered as well. So that's really a good example of what you can expect when you work above 6 gigahertz, between 6 and 7 gigahertz. On slide 22, which is coming, we are zooming in on these two carriers at 6.5 gigahertz and 10 megahertz above. And I think everybody should have this on the screen now. You see 61 dBc IMD3 measurement here. On slide 23 and the following slides, on your screen, we show NPR measurements. NPR stands for noise power ratio. The idea of NPR, noise power ratio, is to apply, in the case of a DAC, we define a high power noise and across a wide bandwidth. So it's a broadband high power noise pattern that we create, and at the center of it we create a notch, which is a zero energy notch. And by measuring how deep this notch is compared to the top signal, we are assuming we are measuring, it's like if we would be measuring rejection from adjacent channels to an empty channel. It's a worst case scenario, and NPR is a recognized measurement that you see on many components, and it's a good metric that you can find from various suppliers to compare performance. In this example, we're doing it in the first micro zone. And we are on slide 24, zooming slightly still on NPR measurement in first micro zone. And that's coming in as well. Everybody should have it, so we see a 47.5 dB and noise power ratio measurement here. Still in first micro zone, and we've zoomed into 1 gigahertz to 1.64. I will go quickly to slide 26. So it's a similar measurement now in the second micro zone, between 3.335 gigahertz to 3.465 gigahertz. And there we see 39 dB NPR measurements at frequencies that are relatively high in the S-band area. And that was all the slides I had for today. I think we are open for questions, if you have any.
Thank you, Nicolas, for that. Very interesting. We have had a couple of questions come in. I'm sure there'll be some more coming after the webinar. The first one was, does the sampling clock break through to the output of the DAC at FS, 2FS, etc., as well as the wanted signals?
Okay. I think I can hand on to my colleague Mark Stacker to answer these questions now. Thank you, Renaud.
Hello everyone. So Mark Stacker, I'm the application engineer. I'll be answering the questions. So the first one was about does the clock spurious will appear on the spectrum. So this depends on the mode that's used. If you remember the slide that Nicolas has shown, is time response depending on the mode.
I'll bring that.
So let's just wait let's try to go back. Yeah. So on this slide, this is slide 9.
Number 9.
So you can see the non-return to zero mode, where the time output is simply the sample value during the sampling period. So with this particular mode, the sampling frequency doesn't appear on the output. Then if you look at the return to zero mode, you can see the sampling frequency clearly appears in the time domain output. You see the 50% on, 50% off at the output that brings the sampling frequency on the output. So you will see in the spectrum the F clocks per. And then the next one would be now return to zero. So here again you can see in the time domain the sampling frequency appearing. It has less energy in this mode than the RTZ mode. And finally the OF is basically you are inputting same as RTZ. You have the sampling frequency appearing, but it's brought by the mode. This is something that can be prevented. So from the best one to the worst one on the F clock spheres, an RZ would be the best one. Then it would be an RTZ, then RF, and finally RTZ mode. And that's for the clock spurious. That's by definition of the mode. Then another big parameter that impacts the clock spurious is the phase difference between the two differential outputs of the DAC. Any phase difference there will bring energy to the F clock spurious. So when these DAC are used, and basically any differential output DACs are used, making sure that the difference between the P and N outputs of the differential pair are very well matched, and that includes any balloon that might be used, is key to bring the best performance and reduce this clock spurious.
Okay, that's great. Thank you. We have another couple of questions that I'll probably put into one for you. The first was, is the EV1 2DS400 commercially available now? And is there a space-rated version available? Which also then leads into, can it also be pushed to work in the fourth Nyquist zone at around 8.5 gigahertz?
This is Nicolas. I'll take this one. So the first question is whether this DAC, EV12DS400, is available for space. The answer is no for this particular one. It's a case for the previous one, DS130, but we are, say, skipping one generation. The next one after DS400 that we will start designing will be planned for space. So the answer would be yes to one. What was the rest of the question? So I think the other question was whether this device
could it be pushed to work in the fourth Nyquist zone at around 8.5 gigahertz?
Okay, so this particular EV12DS400, beyond 7 gigahertz, what will happen is you will have more than 3 dB attenuation, but it will not stop working. It will keep working. You will just have more than 3 dB attenuation at 8.5 gigahertz. So usually that means if you are doing a telecommunication system, probably you will not have enough dynamic range for typical modulation techniques that are used in communication between 7 and 8.5 gigahertz. But if you are doing other applications which require less dynamic range, then you could probably still use it. We know this type of application typically would be a synthetic aperture radar for imaging, 3D imagery of the ground, of the Earth, from a satellite or from an aircraft or from a UAV.
Okay, that's great. Thank you. And perhaps, Nicolas, if you could put back up the slide with your contact details on it, in case there are any further questions afterwards. But in the meantime, I'd like to thank Nicolas of E2V for a very insightful presentation, which will be available on the E2V website, www.e2v.com, and also the Electronics World website, electronicsworld.co.uk. It only remains for me to thank you all for your time. Thank you very much. Good afternoon.
Thank you.
Thank you.